Welcome to this webinar on Hyperledger Besu performance. My name is Matthew Whitehead. I'm a principal engineer at Kaleido. As you can tell from my accent, I'm from the UK office in the south of the UK. And I'm also a Hyperledger Besu maintainer. So I contribute to the Besu code base with a specific focus on enterprise-oriented features. And I lead the roadmap direction for enterprise features in Besu. And the purpose of this webinar is to kind of give a recap on where Besu is with performance. People have run performance tests externally, specifically on kind of enterprise QBFT permission chains. People have published papers on that kind of thing. And some of them are a few years old now, and lots of work has been going on, partly by ourselves, partly by the community itself, partly by Besu developers focusing on the public Ethereum chain with performance improvements that have a benefit to enterprise chains as well. So lots has been going on in the Besu space, and we felt like this was a good time to recap where things are and how things have moved on. We thought it was also worth just reminding people, if you want to ask questions afterwards, or come and ask more detailed questions, or just get involved in Besu more generally, Besu has this series of Discord channels broken down into general Besu use, Besu contributors. If you want to start contributing to the code, there is a channel specifically for Besu Enterprise. You'll see my name all over that, as you'd expect. And so, yeah, just wanted to remind people to come and ask questions there if they want to ask more detailed things after the webinar. I also wanted to just, what I'm going to do in this session is do a demo as well as showing some slides. And that's going to be running on the Kaleido platform. So I just thought I'd give a little overview of the fact that we've got 4 Hyperledger Besu nodes running here, which I'm going to be using to run some live performance tests later on, just to kind of show that it's not super difficult to get some fairly good numbers out of Besu now. And this is all running in the Kaleido ad set platform. So let's go back to slides and crack on from there. And I've lost them because they're now in full screen. Wait a second. Okay. So I thought it would be useful to just kind of recap some general EVM performance best practices, as well as a few QBFT general best practices, as part of talking about where Besu's performance is at. I should also say people will be monitoring the questions in the chat and hopefully answering a few of them. I'll pause occasionally for them to kind of read some out, or for me to read them. So do feel free to put questions in the chat. If there's something you really want to ask about, do come off mute and feel free to ask. But there will be times when we'll pause to take questions. So it's important when you're talking about anything with performance to think about what you're measuring, where you're measuring from, what's a consistent point at which to determine the performance of any software. And so in a QBFT enterprise chain, where you might typically have 4 QBFT validators where votes from any 3 are required for a block to be mined, it's useful to think about, well, what's the performance metric I'm actually measuring when I'm looking at the performance of my chain? So it could be the rate that I can successfully get transactions to a node, the rate at which my application can get them across the network into a node's transaction pool, into its mempool. And that might be what I'm interested in. It might be that what I really care about is actually the rate they can get mined into blocks, because that tells me the rate that the miners are voting on new blocks and processing transactions, updating world state, and so on. But what we're going to focus on here, and what most people will probably be thinking about in an enterprise setting, is what's the rate at which I can do all of that, and I can have confirmation of all of that happening back to my application. So what's the rate that I can get receipts for those transactions and actually tick them off in my application, and then not need to worry about them again? I know that they've been persisted to the chain, and I can remove them from my application's memory. I can potentially remove them from my application's data store, because I know that they've they've been reliably delivered to the chain. So it's useful to think about that. And this picture here, this is what we mean when we're doing our performance testing. This total round trip of they've been submitted to the chain, they've been mined into blocks, and the application has had confirmation of that. That counts as one round trip of a transaction. So when we talk about TPS, we mean this whole round trip. It's also useful to just for everyone to have a consistent view of what they're using to exercise a chain. And there are tools available that help us determine the performance of a chain. I'm going to be using this Hyperledger Caliper tool during this presentation because it's a commonly used tool for exercising EVM chains. It runs a number of different scenarios and gives you different TPS numbers for that. And I'm going to be running some additional ones to these as well. Some people ask performance questions on Discord, for example, about I'm seeing performance issues between my application and this Besu QBFT chain. And at that point, it's hard to know if what they mean is they might have bottlenecks in their application or they might have bottlenecks in their chain. And if everyone has awareness of the tools like Caliper, then they're able to at least isolate the application from the mix and determine is their chain running in a performant way by using a consistent tool like Caliper with common configuration that other users will be using. And then decide, well, is it the chain that's got a bottleneck or is it my custom application that I've built? So Caliper is a tool that can be useful for just giving you a good benchmark for your chain's performance, and that's what I'm going to be using. There's also a Hyperledger Firefly performance tool called the Performance CLI. It delivers very similar kind of performance metrics to Hyperledger Caliper, but it submits all of its transactions to the Besu chain through a Hyperledger Firefly stack. So it does things in a slightly different way, but it does exercise an entire Firefly stack, which many Web3 users are using as their integration to the chain. And again, gives you a good measure of what does this whole stack and chain underneath that stack deliver in terms of performance. And then I can move on and look at what's the performance of my application compared to this performance tool. So those are two commonly used tools for measuring performance. I'm going to be using Caliper just because I'm going straight to Besu nodes, and I don't have a Firefly stack in this testing. It's also worth when you're talking about performance, think about how am I going to monitor performance? How am I going to analyze it? What am I going to use to determine where bottlenecks are? So I thought it would be useful to kind of highlight, to recap to users that Besu itself produces a large number of metrics. At the 23.10.2 release, I grabbed the list, and it happened to be kind of over 160 metrics. And you can query which metrics are available by starting Besu and having metrics turned on, and then just doing a REST HTTP call to the metrics port. And that will give you back a list of all the metrics that are available to help you decide how you're going to build things like dashboards and things. I'm going to, when I do some demos later, I'm going to probably be referring to this dashboard a little. If I show you, I've been running some tests recently. So these kind of dashboards are all built off of the Besu native metrics, and they give you all sorts of data around how many transactions are going into blocks, how big is the transaction pool when a test is running, and so on. And these can be really useful to determine things like, well, where are the bottlenecks? Which of the nodes is seeing hotspots and which of them aren't? And again, I just wanted to highlight that it's useful to have awareness of just the availability metrics and whether or not you're going to consume them, how you're going to monitor them, and so on. And the way that those are typically consumed is that you might run something like Prometheus, which will scrape metrics every 15 seconds from multiple Besu endpoints. And then you can have that configured with something like Grafana to push that data into Grafana and build out any number of different dashboards that you find useful. And there are some default kind of Besu dashboards on the Grafana homepages as kind of example dashboards for Besu. So you can start with those, and then customize them, build your own out from there. But it kind of doesn't make sense to be talking about anything with performance unless you're also talking about what are the metrics you're going to gather in order to understand for your chain where are the hotspots. So general performance considerations for any EVM or QBFT environment. There are lots of things to consider, and building a performant Besu chain does require you to consider all of these areas. Any one of them is possibly a bottleneck, and has the potential to dramatically reduce the overall throughput of your chain. I'm not going to try in this hour to cover every single one of them, but I am going to touch on some of them to give examples of where we've seen users with potentially a very performant chain, but their overall kind of TPS numbers have been very low because they haven't kind of been looking at all of these areas and considering every part of the stack, from the application all the way down to the ultimately the disk storage underneath the Besu nodes. So you do need to kind of have a holistic view of your environment in order to achieve a nice performant setup that's going to reliably churn through good transaction numbers for long periods of time. I'm just going to touch on a few of these kind of to highlight why they're important to consider. So one would be that the QBFT algorithm, that it's now generally the recommended algorithm for Besu permission chains. There are kind of intrinsic limits to how much you can scale the number of validators you have in your chain, and that comes from the fact that the message complexity for something like QBFT goes up as a square of the number of nodes. So the sheer amount of messaging between nodes just to propose and confirm a new block goes up exponentially with the number of nodes you add. So it's important to think about how many validators you're going to have in your network, and at what point is that becoming the bottleneck for new blocks to be produced and ultimately transactions to be marked as final. We tend to see numbers kind of less than 10 being the kind of order of magnitude that people look at with QBFT chains. Often four nodes is given as an example of an environment where if you have 4 availability zones, you can have a node in each availability zone, and one whole AZ can go down and you can still be producing blocks. And likewise, 6 nodes is often used where you've got 3 availability zones and you have 2 nodes in each availability zone, and you can still lose an entire AZ and keep producing blocks. With kind of consortium environments where you might have lots of partners who want to participate not only in hosting JSON RPC nodes, but also validators, and you start to have to consider a larger number of nodes. What we tend to recommend is that you don't always have all of those nodes be validators, but you have a kind of a rotation system where if you have 19 parties who all want to run a validator, they're not all validators all of the time. So maybe you have a subset of those nodes are validators, and then you, on a periodic basis, you vote out one of the existing ones and you vote in another one, and so on, and get a kind of a decentralized trust approach that gives everyone the satisfaction that they are having the opportunity to run validators in the chain, but without a permanent kind of high level of message complexity for all blocks being produced by that chain. So that's a good starting point when you're thinking about building a performant chain, is how many validators you're going to have. Another issue that we come across quite frequently is when people are building their own applications, they are not necessarily considering the nonce management for their transactions. And in a typical case, you might see an application that requests the transaction count for the signing address before every transaction, gets that nonce, uses that in the next transaction, and then repeats that over and over again, and so on. And this is adding an entire network round trip for every transaction, which is never going to be the most performant setup you can have. And so what we what we tend to recommend, and this is indeed what you see things like the Caliper tool using, is a kind of a one-off request at a startup, perhaps, to get the transaction count for the sender you're going to be using, and then within your app, doing your own management of the where the nonce value is for each sender that you're using. So querying the chain once and then sending transactions with incrementing nonces, and taking the hit of a little bit more complexity in your application to, when you get transaction receipts and you determine that a transaction has been finalized, to mark that nonce as confirmed on chain. It doesn't need resubmitting. It hasn't been lost from a TX pool and needs resending. But that slight addition of complexity to your application means that you can build a much more performant environment. And if you're not doing this, you're not going to have the kind of numbers that we're going to see later in the slides. A very similar issue comes up when applications are estimating the gas for a transaction every time before they submit. Now, it's useful. Well, it's critical that a transaction includes a gas amount, but it doesn't have to be precise in a permission chain necessarily, because the amount of gas you use in a public chain is linked to literally a kind of an Ethereum, an ETH dollar cost, and you want to limit that. But in a free chain with free gas, it's not critical that the gas that you assign to each transaction is absolutely precise. And so again, if you're looking to achieve performant EVM numbers from your Web3 apps, it's important to submit a sensible. It can be a big gas estimate. It can't be kind of semi-infinite. It can't be the maximum value, because the way that Besu works is it will assume that each transaction could fill up the whole block. So you don't want to be setting it to the maximum value of OX1 FFF you can see there, but setting it really big is perfectly fine. And when each transaction goes into the block's gas limit will only be reduced by the amount that the transaction actually needed, not by the amount that you set for the transaction. So setting a big, not infinite gas estimate for each transaction manually is a perfectly acceptable way of submitting transactions to a permission chain, and avoids the need to call the ETH estimate gas RPC method for every transaction. We also have to look at what the block period for the chain is going to be. As you increase the block period, you do see some reduction in the message load from that consensus algorithm, the complexity we saw earlier. Because if you're only mining a block every 10 seconds, you're only sending all of those messages every 10 seconds. If you're mining a block every 1 second, you're sending them all every 1 second. And so the network and message complexity does reduce as you increase the block period. As you increase the block period, you also increase latency for your transactions. So the average latency for a 10-second block per transaction can never be less than 5 seconds. So you need to bear that in mind. And also, as you increase the block period, you're also increasing the memory consumption on the node, because the node is going to keep in its mempool all the transactions that it's provisionally decided are going to go into that block, but it won't remove them from the pool unless they've actually been put into a block. So if your node is waiting 10 seconds to propose a block, every transaction that you execute during that time stays in memory until the block is actually accepted. So it's important to think about block period. We tend to do all our testing with 2-second block periods. That kind of gives a good balance of latency versus memory consumption versus message complexity. And that's what I'm going to be using here. But it's important to look, if you're using the default of 5 seconds, you may be unable to achieve high throughput because just memory constraints on your system. So thinking about block period is an important part of a performance chain. Related to that, and generally on the kind of the resource consumption related to the TX pool. So the size of the transaction pool.
Hey Matt, can we pause
sure.
right here?
Yeah, of course.
For some questions.
Sure.
I'm going to let Mark share them with you now.
Yeah, I'm just having a quick look at the chat as well. Okay.
Yeah, Matt, a couple that came up. One, if you need lots of validators, would IBFT or QBFT be better?
Yeah, so that's a good question. So IBFT and after it IBFT2 and then QBFT, kind of evolving iterations of the BFT algorithms. QBFT is the more efficient of all of them. It has improvements that reduce message complexity compared to IBFT2 for certain cases when a round change takes place. So generally our recommendation is QBFT regardless of the number of validators. And in certain cases, it will be measurably better than IBFT in certain scenarios. So we'd certainly recommend QBFT, but there isn't a fundamental difference in those numbers of validators I talked about. You're still going to be wanting to keep within the high single digits, kind of maybe at most kind of 10 to 20 numbers ultimately.
Cool. And then one other question that came up earlier, how many transactions are included in each block and how is that determined?
Yeah, it's a very good question. So the next few slides, we'll talk about that a bit. So what I might do is try and answer that in the next few in the next few slides, if that's okay. And then the person who asked that, if you're able to drop something in if you feel like you need a bit more clarification in a few slides time, please feel free to do that.
Awesome. Thanks, Matt.
Thanks. Okay, I'll crack on for now, and then we will go from there. I'm just going to close the window for now. So let's look at how transactions are included in blocks. The transaction pool size is the number of transactions that can be stored in memory, remember, in between having been received by an application or from an application and mined into a block with the state change for those transactions having been persisted to disk. So new transactions come into the sequence transaction pool, and as they're mined, they go out, and the default size is 4,096 transactions. And you have to look at that number in the context of the block period we just talked about. So if you think about the case where you have a 2-second block period, for that 2 seconds, you could never have more than 4,096 transactions in the block. That would be a hard upper limit. It's not going to be achievable, a 4,000 transactions per block limit, but the hard upper limit for a 2-second block is going to be 4,096 transactions. So that sets a hard limit and limits the amount of memory that your node is going to use. So setting the transaction pool size is a useful way of preventing a Besu node having an out of memory issue. As they come in, so the sequence pool, I'll touch on a little bit later. The sequence pool is what we recommend using in enterprise cases with QBFT. The way that the sequence pool works is more or less transactions are treated in a FIFO order. So when a transaction comes in, it is almost always going to be processed before a transaction that comes into the pool after it. And typically what happens is the transaction pool goes through the list in FIFO order. It does a few basic sanity checks on the transaction to see if it could feasibly fit into the block. So I talked about the gas estimate earlier. If you set the gas size to be the maximum value, and there's already one transaction in the block, Besu will disregard transaction 2 because it will think that I might need all of that gas because that's what the transaction has told me, and so I'm not even going to try and execute this one. So that's why the estimates for gas need to be much less than the maximum value. But ultimately, and if their gas price matches the chain, and if it's a free gas chain of 0, then a gas price of 0 is always going to meet that criteria. And the gas estimate fits within the remaining space in the block, then that's more or less the only checks that the sequence pool does in order to see if a transaction can go into a block. So more or less, they go in FIFO order, and that happens for the 2-second block period. And once that block period is up, then the node goes, right, I'm going to stop processing. Wherever I got to in the pool, I'm going to stop processing new transactions. and I'm going to propose this block to the other validators, and that's where the validators decide if this block is actually going to be mined. So that's how they're selected, and that selection goes on for the block period of, let's say, 2 seconds, and before it ceases. And anything in the pool at that point that hasn't been processed will just wait until the next block. So there's no issue with not getting included in one block. You'll still be a candidate for the next block. And remember that transaction pool content is shared across all the validators. So in this picture, all the transactions come to validator 1, but that validator 1 then tells everyone else, tells 2 and 4 typically, and then they tell 3, depending on exactly how the nodes are connected. They'll all have a very similar looking transaction pool at any one time. So a transaction that doesn't get included in the block will be a candidate for the next block, regardless of the validator that's mining it. What we have to consider there is the subtlety around the fact that Besu has its origins in public chains, where you have to assume you're going to have a large number of unique accounts, unique senders who are sending transactions. And typically, you're not going to have many of those accounts sending lots of transactions at once, because on a public chain, you have to pay for that. That behavior kind of has carried over into the enterprise space, and we've been doing work to kind of change that behavior, because it's probably not nearly as relevant in an enterprise permission chain. But we still have a default that's quite low, where if you don't set anything else, the proportion of that transaction pool that one sender can fill is a very small number, 0.01 or 1% of the pool. Once any sending account has used up its quota of the pool, then it doesn't matter if the rest of the pool is free, that sender can't send anything else until those transactions have been mined. So we need to consider increasing that value if we're going to have a small number of signing accounts. If we have lots of signing accounts, maybe we have a unique signing account per transaction. This isn't going to be a problem, but typically you're going to have a smaller number of accounts in an enterprise setting. So you need to be increasing the percentage using this flag TX pool limit by account percentage. Once you do that, then you're allowing each sender to have a bigger proportion of the pool. You probably don't want it to be 100%, because that would potentially stop other senders getting their transactions in. But having a nice large value where that sender can get a lot into the pool is a good place to start. And if you don't do that, again, you're not going to see any of the numbers, anything like I'm going to be showing later on. Then generally, just system resources. I've not gone, as you can see, I've not gone super detailed on this. When you're looking at the resources you need for a Besu node, it's a JVM-based Ethereum client. It does need of the order of kind of 6 to 8 gigs of memory. And if you go up to kind of 16, there are extra flags you can turn on, which effectively cache more blocks in memory for querying things like receipts. And it's important to think about, when you're running in containers, whether or not the container is actually getting access to all of that memory. There are flags on modern JVMs, things like the one I've mentioned there, the max RAM percentage, which you can use inside containers to set a percentage of the overall RAM that the JVM will get. And so typically, we'd recommend setting that to something like 70 or 75%. That still prevents the node getting an out of memory issue in most cases, but it makes sure it's got plenty of memory in order to do things like storing those 4,096 transactions in its pool. So you want to be kind of these kind of numbers. 2 CPUs, 8 gigabytes is where you want to be at, really. You can go above that. You get kind of slight diminishing returns for that. But just as a ballpark, these are the kind of system sizes that we run with when we're doing performance testing. Okay, so I'm going to show kind of what we're seeing in terms of performance with Besu at the moment. I just thought I'd pause there for any other questions. Oh yeah, so some discussion about IBFT and QBFT validators. Yeah, so you'll see numbers mentioned of validators up to kind of 30. Yeah, it's possible. It's unlikely you're going to get really good performance, but there's nothing to stop you doing that. And there's someone, oh yeah, so Mezian, hi Mezian, one of the other performance specialists from the Besu community is providing a bit of extra detail about estimate gas, which is really useful. Thank you, Mezian. Okay, so close the question and chat window again. So generally, what's been going on with Besu performance recently? So, I said this was going to be a recap of where performance is. There's been a whole load of things going on with Besu generally. The Besu maintainers are always working to improve Besu performance for public chains. I've put a wiki link there, not so much that you're going to type that out, but more just to raise awareness that on the Besu wiki, there are lots of pages. There's one specifically about performance improvements, what's been delivered recently, what benefits they have in what scenarios. More generally, I talked about leading the enterprise roadmap. It's certainly been a focus for us and our clients to see that Besu is spending time looking at performance. Part of the kind of technical work there is involved things like profiling the JVM, and I'm going to show some of that in a minute, trying to identify existing bottlenecks, recommending tuning options and configuration, just generally running a lot of tests, looking at a lot of diagnostic data, and understanding what the kind of current limits are for typical QBF chains. So with that in mind, these are the kind of scenarios that we use as a reference. So again, I talked about the fact that I use Hyperledger Caliper for our testing. So all of the numbers you'll see here will be based on 4 QBFT Besu validators running in the same AWS region, anywhere from 1 Caliper instance to 2 Caliper instances, partly because 2 lets you show some numbers for, well, what if I submit transactions to different nodes? And that's useful to give you an idea for the overall chain performance. If you're sharing that chain with other enterprise users in a consortium, what can the overall chain achieve? And then the case where we use multiple Caliper instances to submit to 1 Besu validator, that's kind of just a replacement for having 1 huge AWS system running 1 really highly performant Caliper. We can kind of emulate that by having more than 1 Caliper driving traffic at the same node. So this is what you'll see referenced across the following slides in terms of performance. In terms of the actual tests that Caliper runs, there are kind of 2 categories. So the ones that I mentioned earlier on in the slides, the default tests that Caliper runs include kind of opening an account in a smart contract, transferring between accounts, and a no state change, just query test, which is has much higher TPS because it's not actually changing any state. So those numbers there are what you get when you run Caliper by default, and we have some numbers to show for those. And again, the previous benchmarks typically were around the 400 TPS for that. And then you can run Caliper with your own custom configuration. And so what's possibly more interesting to most audiences, most people understand what an ERC20 token is. So we also run tests where we use ERC20 tokens to get performance numbers for that, because that's a very common enterprise scenario. And again, previous benchmarks, just to level set what we're going to show later, typically benchmarks show less than 400 TPS for those in testing before now. So in terms of Java profiling, what we look at when we're trying to understand bottlenecks, this is what's called a flame graph of the Besu node JVM when it's running, and the stacks of the tool stacks are kind of calls into Java methods, and they're calls into sub methods and so on. So the taller the stack, the more methods each function is called into. And we can use these to understand which areas of the code is the JVM spending the most time. So which basic EVM functionality is the node doing most of when we're running a performance test. And you can see this actually was kindly produced by Mezian, who's on the chat, kind of an example of what a flame graph breakdown looks like when you analyze it and you look at the classes involved. So each area of the flame graph shows, well, the width is the amount of time spent typically doing that thing. So we can see the right-hand side, we see a lot of time spent propagating those transactions to other validators. We see a fair amount of time spent processing the blocks. Selecting transactions, it's surprisingly kind of small amount of time. And then there's peer-to-peer messaging that goes on between the nodes. Again, that kind of takes up a fair amount of the JVM time. So we can start to build a picture of what's the JVM spending most of its time doing, and how can we optimize those areas. One of the areas that we spent most of the time looking at in the most recent testing is that in some of our test cases, we were seeing a big proportion of the JVM time being spent managing JSON RPC calls to the get transaction receipt call. So when Caliper, typically any Web3 application, sends a transaction, in order to determine if the transaction has been successful, it needs to get the receipt for the transaction when a block has been mined, and just check that the transaction status is successful. And so before an application can mark that transaction as finalized and move on to the next one, it needs to issue this call. And you can see here that what we were seeing was very, very high amounts of time spent in the JVM processing those receipt requests. So that gave us a really good idea for where we were spending a lot of time in the JVM, and that led us to one of the settings in Besu that's not very well known, actually, is only recently documented, which is actually an option to keep in memory a number of recent blocks, so that when an application does a get transaction receipt call, Besu doesn't have to go to disk to get the receipt for that transaction. It's actually already in memory, and that dramatically reduces the amount of time that we're spending in the JVM. So what we recommend is that if you're setting up a perform Besu system, that you're setting the cache last blocks option. It doesn't need to be huge. Typically, you're getting transactions into a block, and then you're probably querying receipts for block the current head of the chain -1 or -2 blocks, but probably not much more than that. So it might only be 4 or 8 blocks that you need to set that to. But we found that gave us quite a bump in the performance numbers that we're going to show you. Other recommendations, some of these taken from that Besu wiki page, things like ensuring that the JVM JMalloc feature is installed and available, and the Besu logs show that that's actually been picked up by the JVM. Configuring the transaction pool appropriately. I mentioned the fact that for enterprises, we recommend the sequence pool, which has that more FIFO behavior. Setting the transaction pool size. If you have the RAM available on your system, then when there are fluctuations, perhaps there's a little blip in the network, having a large transaction pool size allows the node to accommodate that by storing up more transactions during that blip, and still then mining those into blocks and settling down again. So it kind of smoothing out peaks and troughs in the CPU on the Caliper system, the CPU on the other QBFT nodes. A large transaction pool size means you're not going to hit an issue where the transaction pool is full quite as often. But you do need to make sure that you've got the memory to accommodate that. Then I talked about the account limit. So per account, how much of the pool are you happy to be used by single signing signing account? So in the test we run with 0.5, which means 50% of that 8192 transaction pool size can be used by one single signer. That may not be what you want in a true production system, but if you're just trying to prove the ability of the chain, then that means that your sending account from Caliper can really drive traffic into that node, and it's not going to hit limits on the transaction pool size. It's only going to hit limits elsewhere. It's also worth saying that support for the Bonsai database format, which is known to be more performant for certainly querying state. That's only recently been kind of, I guess, hardened a bit more for QBFT environments. So enabling data storage format Bonsai for a QBFT chain is certainly something we have tried. We don't run with it in production systems yet because it's still kind of being proved out. It's only recently, like I say, in 24.7.0, fixes to make that work were included. So only very recently have we started to see that it's fairly stable. But we've got some numbers in these slides which show what happens if you use the Bonsai DB format instead of the Forest DB, and the benefits from some of the state reads that take place. So I think what I'm probably going to do, I'm going to go through a couple more slides, and then I do want to switch to a demo just because it's nice to have a break from just someone talking over slides. But just to give you some numbers, some initial numbers on these are non-ERC20 to begin with cache blocks set to 32, and pretty much all those other options I mentioned except Bonsai for these tests. We're seeing numbers that you can see at the bottom of this screen shows some rough numbers for local development system with 4 nodes. And we've been quite easily able to hit 650 TPS with a local set of 4 validators doing the Caliper open transactions. So it's hitting a smart contract. It is making state changes, but it's not a fully ERC20 contract. And then when we bumped up further now, actually we found we've been hitting much higher numbers than that. We've been able to actually drive that up even further. And on local systems, we've been able to run at nearly 800 TPS for 4 local validators with Caliper running on the same system. So these aren't in AWS yet. We'll show you those in a moment. But this gives you an idea for where we're starting to see some of the performance in Besu at the moment. Again, for the non-ERC cases, these just add a little bit of detail to that and where you start to see the performance really drop off. So having tuned Besu to cache blocks for receipt querying, and we actually see in certain cases that we're able to drive in certain cases close to 1,000 TPS as we drive up the number of Caliper instances. And then we start to see, as you can see, the right-hand sides of these kind of hockey stick shapes. Above that, we start to see the Besu nodes become much less stable. The transaction pool occasionally fills up. Caliper has to back off, and then things really drop off. But you can see that we have quite good stability going up to near the 1,000 TPS mark in kind of just local laptop, well configured, but just kind of basic test scenarios. So then moving on to what those basic, again, non-ERC20 for now, what those basic performance numbers look like when you roll out a four node chain into AWS with Caliper running in the same region. And go back a minute. And again, in that sort of environment, we are seeing stability up to around the 750 TPS mark. Latency slowly grows with that. You can see that these numbers show how big the block sizes are, how big the transaction pool is growing. So again, towards the far right of this, we can see that the orange line, the transaction pool size effectively is hitting over 2,500, well, nearly 2,500 transactions in the pool at any one time. So that's where we start to see those bigger numbers we configured for the pool not being so silly. And these show you the system resources for that kind of setup. And you can see, particularly the CPU line, that one node is taking the brunt of that work. And that's the node that all of these transactions are being submitted to. So we can see that those orange mounds, if I go one slide further, at 700 TPS, we can see one of the nodes is really doing a lot of the heavy lifting on the CPU front, because it's not only mining blocks every 4th block, it's doing all of the JSON RPC processing for every transaction, and it's initiating every outbound message to the other validators to say, here's another transaction for your pool. If we then look at, well, what if we in AWS, what if we run 2 calipers pointing at the same node? So this is one Besu node out of the 4 doing all that work again, but we've kind of increased the system resources for Caliper by just doubling how many EC2 instances we use. And again, we see that actually we can continue driving the chain up into the 900s with that that one node still doing a lot of the heavy lifting. If I go to here, I think we also sorry, I'll go back for a second. Yeah, we see that we can still drive a lot more traffic into that one node if we increase the amount of resource on the Caliper on the application side. And here, look at the orange line on the left is showing that the pending transaction count is now getting close to 3,000 once we have those kind of high numbers. If you look at sharing some of that CPU load across the node, so if you look top right of this slide, you can see now we've got the same two calipers, but we're sending transactions to two of the nodes. So we're sharing some of the load now for the JSON RPC calls. And this starts to give you a feel for the chain as a whole, the performance for all participants when they're sending things into various validators. We're seeing numbers where we have kind of stability up to around the 1200 TPS mark for those kind of scenarios. Again, all of this is still non-ERC20, but it's still smart contract invocations and state changes on the chain. And the transaction pool sizes are now kind of just peaking above 4,000, that orange line on the left-hand chart again. And so these are some of the numbers we're starting to see now, which is I think really exciting for where Besu is at. And I'm going to show ERC20 as I said in a minute. For that case where we've sent transactions to two nodes rather than one, you can see that CPU line, the third chart, as we hit the far right, the 1200 TPS numbers. Now we see two of those nodes doing that heavy lifting. We see two of those nodes doing the bulk of the CPU work to process transactions and share them out amongst the other nodes. And you can see that we've not run tests where we've driven traffic into all four nodes, but I think we would see probably even higher overall TPS across the chain itself if we're sharing more of that work across all four nodes. So we kind of scaled to look at what does two nodes processing transactions look like. And I think you'd see that will grow potentially even further if you're driving traffic into all of those nodes, which most enterprise use cases would be, because people running nodes are going to be typically using them. Okay, ERC20 performance. I do want to touch on that. I think so. All my demo is going to be ERC20, which is why I've not jumped straight into it for now. But I'm now just going to switch out. I think I'll just do one check for questions before I do that. Looks like mostly questions about the recording. Madison or Mark, shout if you've seen anything else.
One recent one, we use a load balancer in front of the validators. Any thoughts on that?
Yeah, so using a load balancer for sending your transactions into the nodes, it's not something we've tested in these scenarios. There's no real downside to doing that particularly that I'm aware of. Obviously your subscriptions, if you have filter subscriptions to get notified about new blocks, you're gonna want those to be on just one of the nodes, so that effectively that filter subscription stays kind of consistent and isn't being recreated on different nodes when you restart. But for sending transactions into the chain, then there isn't really a disadvantage to distributing them out. You might find, perversely, that performance is better going into just one node. It's not totally easy to say, but if you imagine the case where transaction one for a given sender goes to validator one, and if that's the one that's mining the next block, and you send transaction two to validator two, then it's got to make its way back from validator two, and transaction three is going to validator three potentially, and so it's kind of hard to say for certain without actually probably running some of these tests yourselves to see which is the better performant one. Yeah, typically it's unlikely to do you any harm, I don't think.
Okay, and then we've also, I think, unmuted, is it Bizer for a question?
Sure. Hi, Bizer.
Hey, not sure if
Yeah, can hear you.
can you hear me?
Yeah, we can hear you. Can you hear us?
Okay, yeah. Sorry, there was a Zoom issue here. So a question I have is, and it's Alton from Citi. How does the picture change if you were to consider that instead of sending the transaction requests over to these validators, right, 1 or 2 or 3 or 4, you send them to 4 RPC nodes, and you would have, let's say, 8 validators in each of 4 data centers. So all the transaction requests would be intercepted, if you will, or round robin load balanced across 4 RPC nodes, and everything else is handled by the peer-to-peer.
Yeah, it's a very good question. So you're kind of, I guess, referring to the fact that you could try and offload some of the CPU work to nodes that aren't producing blocks, but they're just doing the JSON RPC validation, and you're kind of retaining more of the CPU cycles on the validators for worrying about producing blocks. I guess that's what you're kind of referring to.
Yeah.
Yeah. I have run that kind of setup. It hasn't shown particularly big performance improvements over going straight to the validators. I haven't spent huge amounts of time investigating the reasons for that, but it is a scenario I've run. I had some slides actually kind of specifically on that, but because we had found it didn't show particularly any notable improvements. And if you've got enough resource on those validator machines, then it's not something that's leapt out as an obvious improvement to QBFT performance, put it that way.
Okay, thank you.
No problem. Right, I'm going to just switch demo now, just because we're not got loads of time left. I've not got loads of demo to show, but I just wanted to show something. So these are my 2 caliper windows. Mark, I'm going to rely on you to tell me that you can see these actually. And again, these are going to those 4 nodes I showed on the Kaleido platform. So just to give you kind of a basic idea of what the caliper output looks like, this is going to just run a 350 TPS test. It'll be fairly short against one of those nodes. And for those of you who aren't familiar with caliper, this is the kind of output you get. So this is the RC20. And so you see the first part of the test is just minting some tokens. So we just do a few of those. And then the lines that you're starting to see here, apologies if the text is quite small. I tried to make it bigger, but then it was all word wrapping and it was kind of harder to see. But this is just showing you how many transactions have been successful. The unfinished count is kind of proportional to what's in the transaction pool. And the way that Caliper runs these tests is and this will be doing, I think, just about 15,000, maybe 20,000 tests. So just take another few seconds. So we can just show you a 350 TPS test against one of those nodes. And that should be coming out in just a second. While that is finishing off, this is my dashboard. I'm just going to switch that back to 2 minutes. And this is where you'd probably want to have your dashboard showing you, okay, so what am I seeing for my nodes? What's the system resource usage looking like on CPU load on the nodes and so on. And that's kind of a key part of this this kind of performance test. And so there we are. So we've set it at 350. I'm going to see if I can annotate this, if it will let me. Okay, so you can, whoa, let's clear that. What I want is, I think I want this. So the send rate over here is 350. We don't achieve quite that. We achieve 338 TPS. But roughly speaking, our 350 TPS run has gone through okay. And if we increase that, it's going to increase the overall view. That 338 on the right hand side is not kind of a hard limit, just kind of a facet of the way the caliper's behaving. And then we can do the same. We can run a 450 test against the same chain, and we'll just see how, as we increase the throughput from a single caliper instance, we do slowly see improvements. But we have kind of some upper limits around the numbers that we were seeing. And I should say that I showed you all the non-ERC20 performance numbers in the charts. The ERC20 numbers are generally slightly lower. They're good, but we're not. This demo is not to show you a wow. We're kind of even faster with ERC20. ERC20 does a bit more in terms of state reads and state writes. And so the overall TPS is going to be slightly lower than the numbers I was showing on the slides, but we still see some pretty good performance. And you can see these submitted and successful rates are going through at a pretty good rate. 15,000 transactions successful, 16,000. And in a second, we'll hit 20,000 and our test will be done. And let that just collate the results. Okay, so that 450 test, I'll just try and highlight these to make it as clear as possible. So our send rate there was 439 in the end. Again, we're probably starting to see some limits of the system that we're running caliper on. And our overall throughput 425 is not too bad. That's kind of comfortably above the less than 400 that we were seeing kind of generally over the last couple of years. What I want to do though is really I want to run 2 of those across my 2 calipers along the lines of the test that I showed you earlier. So this is now 2 ERC20 runs, and we're going to run those concurrently against the same node. So these are going to the same node. We're going to let those chug through while that runs. I'm just going to switch back to the metrics and just show that we're for those previous runs, we were seeing of the order of 1,000 transactions in the pool at any one time. And we kind of peaked around the 1,000 transactions in a given block. What you tend to find, I'm running these for, I think, 20,000 transactions, I said. We tend to find if you run for longer, our 100,000 transaction tests show better overall TPS as the JVM kind of warms up a bit. And the performance just slowly grows over a longer test. So 10,000 or 20,000 transactions doesn't show the absolute best that the chain can do, but it still gives a pretty good indication. So I'll switch back to these, and we've got try and make that screen a little smaller so we can get it all on one screen. So these 2 screens are now going to show their results. And what we see here is, if I highlight all of these, so we had both of the calipers sending just under the 400 mark, and the resulting overall TPS, so again, a little bit under the 400 mark, but comfortably over 700 TPS if you sum those numbers, kind of pushing on for, you know, I think we'd be getting towards 750 TPS, pushing all of that traffic into a single node. So the actual numbers that we're starting to see for kind of the latest versions of Besu, if I go back to slides now, window. Sorry, clear some annotations. Okay, and okay, so yeah, here is really where our numbers are at as a summary for ERC20 performance for those topologies that I've been using throughout the slides. So broadly speaking, we can hit over 500 TPS with a single application driving into one node. We can comfortably hit over 700. I didn't push that particularly hard, that test. And again, I ran them for fairly short periods of time, but we can comfortably hit over 700 if everything from 2 applications goes into one node. And again, we can bump that further, 750 plus, if we are distributing that load across the validators. We've also done some of those tests again with the Bonsai support that's gone in. So we've done some experiments with Bonsai to see how that is affecting those numbers. And again, just very basic tests that we've run just to give an early indication show that again we see some bumps again on those numbers just by turning on Bonsai. So with no extra work, no more profiling with Bonsai to see are there any obvious bottlenecks, that kind of thing, just turning it on. And we're seeing close to 800 TPS through a single validator in a 4-node chain. We hit 800 TPS going into 2 nodes. So what we expect to see as the Bonsai support stabilizes, that becomes what we recommend as a database structure. And that it should be even easier for us to be hitting these numbers, and kind of to draw you back to where I was talking at the beginning of the slides around where was Besu around the 400 mark, probably less than 400 mark for ERC20, 400 mark for the more basic caliper tests. These are some really promising numbers that we're now seeing without having to kind of really finely tune, just paying attention to all those things I talked about, and making sure some of those basic configuration options are set appropriately. Okay, I'm almost out of slides. I know I'm out of time. I'm almost out of slides. So I just want to cover a couple of last things before I finish. People will be saying, okay, so how do we go kind of into the 1,000 and beyond? So there is going to be further work on performance generally. We will see those numbers climb, I believe. What we do know is they're never going to go orders of magnitude higher. We know that the nature of a BFT protocol, the amount of messaging between nodes, the fact that you're effectively replicating state in several places, we're not going to see huge orders of magnitude increases. We'll see some steady improvements. What we're seeing enterprises look at is how can we grow our overall TPS count then? And one strategy people are using in the wild in production is to actually batch business transactions inside individual EVM Besu transactions. So a Besu transaction with not zero might contain several business transactions. Now that does mean, if I go on to the next slide, it does mean that the smart contracts you're invoking need to be able to support batching. They need to be aware that they're going to get a batch of things, not just one thing. And so it requires kind of custom smart contracts. And it requires your applications to be aware of how do I batch transactions and how do I handle, handling the acknowledgement for all these transactions and marking those all off. There is some extra complexity to this, but it's a technique people are looking at with EVM platforms to see where they can push their overall business transactions per second. And our own testing of this shows that you can do that very successfully, and you can reach numbers that this chart shows. So it tails off because as you increase batch size, you're still processing lots of state changes. And you're potentially submitting very large transactions and so on. So it does tail off fairly quickly. But if we look at the case where we batch 500 business transactions into a single Besu transaction, we can see that we have an overall transaction rate of 7,500 TPS. And this is one of the techniques people are combining with the general underlying performance of Besu transactions to achieve pretty good production business TPS for their enterprises. And I wanted to touch on this as something that we have spent some time looking at, running performance tests for, and highlighting as one technique, one strategy for increasing overall throughput through an EVM chain. Okay, last slide was just say there will be more work going on. We know that there are places we duplicate some of the block processing. We know that we could improve getting block receipts in one call rather than a call per transaction. There is already work going on to look at can you parallelize the transaction processing in Besu, and that's being done. People like Amezian who are on the call lead a lot of really valuable performance enhancement work in Besu itself. So there's lots going on. We expect more to come. So do watch this space, but that's pretty much the end of the slide. Sorry that we've gone a little bit over, but I wanted to try and cram in as much as possible.